Hello and welcome. In this video, we're going to talk about a new type of function, exponential functions. We're going to look at what an exponential function looks like in its standard form. We're going to look at what makes an exponential function a growth function versus a decay function, how exponential functions behave considering their domain and their range, and how they have an asymptote. And then we're going to look at some real-life applications of exponential growth and decay by analyzing some formulas and working through some word problems. So let's go ahead and jump right in. Okay, so let's start with what is an exponential function. An exponential function can be written of the form y or f of x equals ab to the power of x. And the key thing here is that a and b are numbers, and x is actually your input or your variable. And sometimes you're going to see a t here instead of an x if we're talking about something with respect to time. So actually I'm going to use a different color. So x is our input. We plug in an x, we raise b to that power, and then multiply it by a, and that will give us our output, our f of x or our y. So the key thing with an exponential function is that our input variable x is the exponent. Now there's a couple other little details up here that I do want to point out. It says that a is not equal to 0. Well, what would happen if a was equal to 0? This function would just be the constant function 0. So a is actually our initial value, because if we plug in, let's say 0 initially, here b, whatever that number is, to the power of 0 is going to be 1, so we're just left with a. A is the initial amount, or the y-intercept, you could think about it as if we're talking about the graph. B also gives us some important information. B tells us if we have a function that is representing growth or decay. Think about that. If I had something like 2 to the power of x, and let's just start plugging in numbers. If I plug in 0, I get 1. If I plug in 1, I get 2. If I plug in 2, I get 4. If I plug in 3, I get 8. It is growing. Every number is getting a little bit bigger. So if b, and it says this right here, but if b is greater than 1, then we're talking about growth. Now let's pretend that b is less than 1. If b is less than 1, let's just pick a number like 1/2, and we're plugging in x's. If I plug in 0, I get 1. If I plug in 1, I get 1/2. If I plug in 2, I get 1/4. If I plug in 3, I get 1/8. All of these numbers are getting smaller, and that's why if b is less than 1, we get decay. Now you might be wondering, we have something that talks about what happens if b is greater than 1. We have something that talks about what happens if b is less than 1. What happens if b is equal to 1? Well, up here it does say other than 1, but let's see why that condition needs to be there. If b is equal to 1, 1 to the power of x is always going to be 1, which means our function would really just be a times 1, and that's not exponential anymore because we don't have a variable. So key things, x is our exponent, and that is what makes this an exponential function. B, that value of b tells us if we're growing or decaying, growing if it's greater than 1, decaying if it's less than 1. And if there is an integer or a value in front in the a spot, that's giving us our initial condition, which is just what happens when we plug in 0. So let's talk in more detail about what these functions look like graphically. So let's first talk about exponential growth. And we already said, but I'm going to just make a note of it here again, that growth happens when b is greater than 1. It also needs to be that a is positive, but we're really just going to focus on the form where a is 1 because that's the most basic form with no stretches or shrinks. So we're going to think about the parent function. So if b is greater than 1, then we have an exponential growth function. B is called the growth factor. That's going to relate to the rate at which something is growing. B is going to be greater than 1 because, again, we're talking about growth here. Things to notice about the graph. Now, if we plug in 0, we're going to get 1. We already said that a is 1 in this case. And also, when you look at the graph, since it's increasing, it's going to look like your graph is going uphill. If I put a little person here, this person is walking upward. It's growing. The angle at which the person is walking is growing. It rises from the left to the right. The domain, thinking about what we're allowed to put in, we don't have square roots or cube roots or fourth roots or anything else to worry about here. We're allowed to plug in positive numbers. We're allowed to plug in negative numbers. We're allowed to plug in 0, so our domain is all real numbers. Our range, thinking about our output, So even if I plugged in, I'm going to go back to my example with 2. Even if I plugged in a negative number, remember, if I put 2 to the power of negative 1, I get 1/2. If I put 2 to the power of negative 4, I get 1/16. So based on this model where b is greater than 1 and a is 1, we're never going to have any negative numbers come out, which you can see from the graph. The graph never goes below this x-axis. We're also never going to get 0. There's no value of b, if b is greater than 1, that when I put it to a power, I'm going to get 0. So that creates a horizontal asymptote at the x-axis, or at the line y equals 0. So that horizontal asymptote is a line that the graph never crosses. Now, it is possible, and we'll focus on this in another lesson, that this graph is translated up or down. So that horizontal asymptote may not always be at y equals 0, but for the parent function, that's where it's at because it's never going to cross that line. Which is also why the range is from 0 to infinity. And notice that parentheses there, not a square bracket. The range does not have a square bracket because this will never equal 0. It will get really close to 0 and then it will increase after that. Now, it probably won't be super surprising to you that decay is really similar, but again, instead of focusing on b being greater than 1, we're going to focus on b being less than 1. So we're looking at a b value that's between 0 and 1. We're still going to say that a is positive because we're looking at the most basic version of this function. So this is going to be our exponential decay function. So this parent function is exactly the same. We just have a new condition for b. b is less than 1, but also greater than 0. B can be also referred to as the decay factor. And what we're looking at is, notice the domain is the same. So now this function is decreasing from left to right. It's like I could skateboard downhill here. But everything else is pretty much the same. The domain, I'm still allowed to plug in negative numbers, 0, and positive numbers. The range, I'm still going to get really, really close to y equals 0, but I'm never going to cross it. So I still have a horizontal asymptote at y equals 0, and my range is still from 0 up to infinity. So the key thing is really, is it increasing or is it decreasing? The rest of the behavior looks really similar for both of these types of functions. We will focus on using all of these different pieces to graph in a different section, but the point of looking at them here was so that we can understand what that means when we apply it to a word problem or we apply it to a problem that has context. So let's actually look at some examples and see how the exponential functions, how these pieces help us work with those models. All right, here we go. The value of a new car Y in thousands of dollars, where T is the number of years since the new car was approximated, can be modeled by this given model here. And then we're being asked 3 things. Tell whether the model represents growth or decay, identify the annual % increase or decrease in the value of the car, and from the given graph, estimate when the car's value will be $8,000. So let's kind of, before we even jump into solving that, let's make sure we understand all of the different pieces of this model. So 25 times 0.85 to the power of t. In this case, this is an exponential model, and I can tell it's exponential because t is the variable, which means our b value is 0.85 and our initial value a is 25. And remember, 25 actually means $25,000 in the context of this problem. All right, now that we've kind of identified the different parts, the different pieces, so the car's original value was $25,000, we can talk about whether this is growth or decay. So the number inside our b value, so for part A, I'm going to say b is less than 1, since b is equal to 0.85, which means we are talking about exponential decay because b is less than 1. Every value is getting smaller. The percentage of increase or decrease, well, what I want you to think about is 0.85 is how far away from having it be 1, right? 1 would be where we don't have an exponential function anymore. Anything less than 1, or how far away we are from 1, is going to tell us what our percent increase or decrease is. So this is basically saying that the car, every year, we're looking at 85%, 0.85 of its value. So what is the annual increase or decrease? We can really think about it as, how far away am I from 1? So if I'm looking about, or if I'm asking about the rate, I'm looking at 1 minus 0.85 in this case, since it's decay, and that's going to give me 0.15. Now this question asks us for the percentage, so I'm going to rewrite this as a percentage, and I'm going to say decrease. And actually, since this is a word problem, I'm going to come down here and answer this in a complete sentence. The annual percent decrease of the car is 15%, or the car decreases in value 15% each year. All right, last but not least, part C says, from the given graph, estimate when the car's value will be 8,000. So what that's really asking us is, we're trying to figure out what this is, 25 times 0.85 to the power of t. We're looking for when, so we want to find t. Now, we don't know how to solve an equation like this. We will by the end of this chapter, but we don't know how to solve an equation like this, so we're going to look at the graph and see if we can pinpoint where y is equal to 8. So I can see down here that this little point here is when y is equal to 8, and that says that that's happening when x is equal to 7, or you could count the little tick marks there. So after 7 years, the car is worth approximately $8,000. All right, I'm going to put up another example, and I'm going to ask you to try and answer the questions on your own. All right, so here we have number 2, the value of a classic car in thousands of dollars, where T is the number of years after the car was 40 years old, can be approximated using this model. Part A is going to ask you, is it growth or decay? And part B is going to ask you the annual percent increase or decrease in the value of the car. So go ahead and pause the video and answer those 2 questions on your own, and then unpause the video and see how you did. All right, hopefully you had time to work through that. So I'm looking at B to tell me if I'm growth or decay. So for part A, since B is equal to 1.25, which is greater than 1, this model represents growth, which makes sense. Classic cars do increase in value once they're no longer made, the further away from the year they were made. Part B says, identify the annual percent increase or decrease in the value of the car. So again, I'm asking myself, how far away am I from 1? I'm over 1 in this case by 0.25, which means 25%. So the annual percent increase, or the car's value, is increasing at a rate of 25%. So oftentimes we want to really be able to focus on that rate and how things are changing. And in the current form that it's written, we are identifying that by comparing the number inside, whether it's growth or decay, to 1. And that's telling us what our growth and decay rate are. And that leads us to the model that you'll more commonly see used in the context of a problem like this, where we're talking about exponential growth or decay in a real world application. So let's go ahead and look at those models. So I want to point out here that these are really exactly what we were just doing. What we just did to find B was we talked about how 1 related to R, and how, or I guess we talked about how 1 related to B. How far away from B was 1? How far away from 1 was B? That's how we talked about it. So this is really just exactly the same as what we were talking about, but now it's easier to identify the rate from within that. So some real life quantities increase or decrease by a fixed percentage each year. That happens oftentimes with bank accounts, with credit cards, fixed rates of interest, fixed rates of increase and decrease. So noticing this is not different. We still have an A value, that's still our initial amount. We still have a rate, and it's still being put to an exponential power. And again, if we're over 1, we're talking about growth. That's why growth is over here with 1 plus R, and decay is over here with 1 minus R. So now let's look at some examples where we can apply this slightly more specific model than we were looking at before to some word problems. All right, for example 3, in 2000, the world population was about 6.09 billion. During the next 13 years, the population increased, so that's telling me I have growth, by about 1.18% each year. So remember, we're going to be looking for our rate as a decimal. I'm going to actually add that up here. So when I see it written with a percentage symbol, I know I need to divide by 100 or move the decimal places 2 times in order to find that value. So in this case, R is going to be 0.0118. So we're going to write an exponential function to model this situation for t years after the year 2000. So for models, I don't mind if you use f of t or if you use y. It's going to equal the initial amount times our 1 plus our rate, since this is growth. So again, I saw the word increased, so that's telling me growth to the power of t. And since I can simplify that sum in my head, I'm just going to do that here. Important things to note about a model is still going to have a t or an x in it. It is telling you can plug in any t value to find out what the amount is after that time. Part B is where we're going to substitute a number in for t. So estimate the world population in 2005. Well, if this starts in 2000, then 2005 is going to be 5 years later. So we're going to be looking at y equals 6.09 times 1.0118 to the power of 5. We're going to plug that into our calculator, and that's going to give us approximately, since I'm going to round, 6.458, and I'm going to answer this in a complete sentence. In the year 2005, the world population is approximately 6.458 billion people. Make sure you include the word billion there. It's the only reason it actually makes sense for us to have a decimal place here, because we're basically writing this as a more concise number and not having to add on quite so many zeros. All right, let's go ahead and try number 4 on your own. Some tips, some reminders. When I read through the sentences, I always underline and circle and make notes of things as I go so that it's easier to plug them in. Another reminder, take time to make sure you're carefully pushing the right buttons on your calculator. I always double check my answer. If I get the same thing twice, it's usually meaning that I'm typing it in correctly. So pause the video, work through number 4 on your own, and then unpause the video and see how you did. All right, so here we go. My model is over here on the left. My A value, my initial amount is 1.04 million. During the next 14 years, the population increased, so I'm using 1 plus R by about 2.05%. Need to convert that to a decimal, 0.0205. For part A, we're writing the model. For part B, we're estimating the population. I want you to always show the step where I can see this is what you're typing into your calculator. That way, if there's an error after that point, I can make sure that I know that was a calculator error. So when you do this, you get that y is approximately 1.223 million. And I'm going to answer that in a complete sentence as well. I want you to have at least 3 decimal places of accuracy, unless we're talking about money or something that doesn't make any sense to have 3 decimal places. So let's go ahead and write a sentence here. In 2008, the city population will be approximately 1.223 million. And there we have it. Next, we're going to talk about a specific application of exponential decay that shows up a lot in sciences, and that is half-life. Then we're going to wrap up by talking about compound interest. Okay, so here we are told that the amount Y in grams of radioactive isotope chromium-51 remaining after T days can be modeled using this model here, where A is the initial amount. We're being asked for the percent, or we're being asked for the rate as a percent, that it decays each day. Now I want you to look at that function. I want you to identify what's different about that model than all of the ones we have looked at so far. Well, hopefully that you notice that what's different is this exponent has a number. It's not just to the power of t, it's to the power of t over 28. Well, fortunately for us, we know how to manipulate things with exponents. So what we can actually do is separate that exponent into 1 over 28 times t, right? Normally we combine those two exponents, power to power, we multiply. Here we're going to split them into two pieces. By doing that, we can actually raise 0.5 to the power of 1 over 28 on our calculators, which allows us to figure out what the rate is. So here we have, I'm going to give a couple extra decimal places. Let me write that more clearly. So here I have my exponential model. Now what this means is that b is this number here. I want to know what my decay rate is. So I'm going to subtract that value from 1 to figure out at what rate we are decaying. So the rate as a decimal is going to be equal to 0.02445. Then I'm going to write my answer in a sentence. The decay rate is about 2.445% each day. The last type of exponential model we're going to talk about in this lesson is compound interest. And I always remember that compound interest looks the most complicated. The idea of compound interest is that simple interest, you deposit a certain amount in the bank and you earn interest off of that initial amount. So I earn interest off of the $100 I deposit. I'm always only earning interest off of that $100. Compound interest means that we actually earn interest off of our interest. So every time our account is compounded, they're basically recalculating what our A value is. You can think about it in that way. So let's say I deposited $1,000 and then 6 months later, I've earned enough interest to now have $1,100. Now it's going to start calculating interest off of that $1,100. So you earn interest off your interest, which is better because now you're earning more money. You're having a higher amount that's being multiplied. The formula for compound interest is here, and you do need to know all of these formulas. You need to know what they are. You need to know how to use them. You need to have them memorized. You should notice that formula only looks slightly different than this one, and the big difference is that we have this n. So P is really the exact same thing as little a was before. P is the principal or the initial amount. R is still the rate as a decimal. N is the number of times per year that we are compounding the money. You'll know you're doing a compound interest problem if the word literally says something about compounding your interest. So you deposit $9,000, that's the initial amount P, in an account that pays 1.46%, so 0.0146 is our rate, annual interest. Find the balance after 3 years, so we're eventually going to find the balance when T is 3. If the interest is compounded quarterly, how many quarters are there in a year? There are 4. So let's go ahead and write this as a model. A equals our initial amount, 9,000, times 1 plus 0.0146 over 4 to the power of 4t. And for this problem, we actually care about what happens when t is equal to 3. Now, when you type this into your calculator, I recommend that you work from the inside out and you let your calculator do the work. But start by 0.0146 divided by 4. Take that number, add 1. Take that number, raise it to the power of 12. Take that number and multiply it by 9,000. Do it in pieces so that you don't make any mistakes. So go ahead and try that calculation on your own and then unpause the video and see how you did. Then write your answer in a complete sentence. So after 3 years, I have $9,402.21. Go ahead and pause the video and work through number 7 on your own and then unpause the video and see how you did. So hopefully you had time to work through that. Here's our model. Then I'm going to go ahead and plug in 4. Then I'm going to be really careful when I'm plugging in values on my calculator. That's going to get me here. And then I'm going to write that in a complete sentence. After 4 years, the amount of money in the account is $9,066.02. All right, so wrapping up this video, we talked about what an exponential function is, what makes it growth if b is greater than 1, what makes it decay if b is less than 1. We talked about key characteristics of those graphs, but we'll revisit that in another section. And then we applied real-life models of growth and decay in context to word problems. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.